Hello world and welcome back. This is the second part of the exponential function series. So today we're going to focus on a very special number base, that's e. It's approximately 2.7. You can see the approximation down below right here. And but we will go with 2.7. If you look at all of the characteristics on the right there, pretty much everything is the same as any exponential function with a base that's greater than 1. The graph, if you were to show me that graph, I would say that's an exponential function that's increasing with a base that's greater than 1. I wouldn't necessarily know that it's e. They all pretty much look the same. So just memorize that number 2.7 and we'll be good to go. All right, so let's get to graphing these. So look, here's the parent function. So I would like to make a little bit of a table for you. So try to get that going here. X, Y, and then so in this case I'm not going to use any negative numbers because we know that they get small pretty quickly. But it was 0, 1, and 2. Let's use the line straightener. So we know that e to the 0 power, we know what that's going to be. It's going to be 10. Just kidding, it's 1. E to the first power we can estimate to be 2.7, and e squared, I think that you should probably memorize that number. So let's go to a calculator. This should do the job. So if you see e to the first power, that's 2.7 blah blah blah. E to the second power, so yeah, 7.38, so 7.4 should do the job. So why do I need that extra value? I don't know, just to give it a little extra precision. Precision. All right, and there we go. We'll go plot those points. And you saw the parent function in the previous slide. But 2.7. I just want you to have an experience doing this. You should probably be graphing this on your own. So that's 2.7, and then 2. 1, 2, 3, 4, 5, 6, 7.4. And then I'm gonna just go for it. All right, let's get close to that asymptote here. Preparing for liftoff. It looks something like that. Now, all right, just for fun, let's just review the domain again. The domain, all real numbers. Range is going to be numbers that are greater than 0 or 0 to infinity. Let's move on. So this is another variety of e. This time, though, we are going to have a negative in front of our argument. So let's annotate here. The first thing that you're going to want to do is when there's any form of multiplication, is we want to take care of that in terms of our transformations. So right here, step 1, after of course plotting your parent function, is to reflect in y-axis. And then step 2, is going to be, and there's only 2 steps in this one, is to shift up 2 units. All right, so we're going to take all of these special points from the previous. Let's copy that. These are our parent points. And we're going to reflect them in the y-axis. I wish there was a reflection option here with this tool, but there's not. But it's fine. When we reflect in the y-axis, we just count units. 1, 2, 1, 2. 7.4 is now at -2, and then we sketch. So it's a little bit shaky. Okay. It's good enough. Remember, it's a sketch. I mean, if you want to make it like furry like this, I feel like you can kind of round it out some more, but don't bother with that. All right. I made it really furry. Okay. So now we have that blue graph is almost our final graph, and now we need to shift it up 2 units. So what I'm going to do is I'm going to erase the parent now. We don't really need that so much anymore. And then I'm going to just shift our graph up 1, 2. Now, when you move the graph up and down, recall the parent has a horizontal asymptote. So our new horizontal asymptote, which we will color green this time, is going to be at y equals 2. And there it is. So let's state the domain and range just for fun. The domain all reals. Range is going to be 2 to infinity. All right. Now we move on. So there's something called the logistic function. Again, some of you may have heard of this. Now, I mentioned I believe I mentioned in an earlier video that when you're graphing exponential functions, or we're studying exponential functions, and especially if we're modeling real life behavior of things, most phenomena that tends to mimic exponential growth is actually just sort of a close-up of a logistic function, because in reality, like things that grow exponentially, like populations or even a virus that would require hosts of some sort of animal, there's only a finite number of people or animals or whatever. So ultimately, there's going to be what you'd call a carrying capacity, a maximum value that could be obtained. So there's a point of increase as we're exponentially increasing where things change direction, and you would call that an inflection point, like something that you see like right here on our logistic growth function, and things start to level off. So that would be true for almost everything that's exponential on Earth due to finite resources. Okay. So the logistic function that you see stated here is specific to our irrational number, our special number e, although there are other situations as well where you could have a different number base there. But the ones that we're going to study are always increasing. You don't really have logistic. It's technically possible to have logistic decay, I guess, but that'd be weird. I can't think of any examples. So we're really just more interested in the ones that we have increasing and then like a leveling effect. So if you look at this function, if you're asked to graph this, you're not even worried about key points. There's really just 3 key attributes. You want the carrying capacity, the numerator, so to speak, of our this part right here. That's always going to be your horizontal asymptote on the right side. That's your right end behavior. On the left end, there's always a horizontal asymptote that's y equals 0. So you see here on our little fact sheet, this is our left end behavior, and this is our right end behavior. And we get this, in this case, for this particular function, we have the numerator is 1. So, but whatever your numerator is, that's going to be what you'd call your carrying capacity. Like, so that's a right end behavior. So that always comes from the numerator. So you have your right end behavior, your left end behavior, which is always 0, and then the y-intercept. And the y-intercept is always just found by going f of 0. So that gets you that. All right. And everything else is pretty much, just sketching. So let's do a couple of these and we'll call it a video. All right. All right, so this one is not E, right? So it's really important that I show this to you. So as mentioned before, we need to list the three things. We have one, I want to know what's happening as x approaches positive infinity, my right end behavior. So that's going to be, y is going to be approaching 8. Okay, I could write that as a limit if I wanted to, but just for fun, I'm going to do it this way. And so y equals 8 is my horizontal asymptote, only on the right side. I'm going to draw it on both anyway. So we have 1, 2, 3, 4, 5, 6, 7, 8. Just draw a horizontal line, and looks like it landed there pretty well. And we have another one that's going to be our, I'll just put it there, but our x-axis is also on the left-end behavior. So 2, it's just worth stating, as x approaches negative infinity, y will be approaching 0. So in both these cases, you have a horizontal asymptote. This one's y equals 8. This one's y equals 0, left end. And then we need the last thing would be our y-intercept. And so that means we have to evaluate f of 0, which is equals 8 over 1 plus 3, which is 8 over 4, which is 2. Okay. And then you start on the left side here. And it should look something like that. If you wanted to verify something like this, if you don't believe me or whatever, you can just go to like Desmos or something and graph it and see. It's gonna pretty much do that. And that's all you really need to know for this. Let's take a moment though, and I knew that would happen. Let's take a moment and state the domain and range. Let me move this out of the way. Okay, so our domain appears to be all real numbers, right? If you look at the little fact sheet, that's the deal. And then the range, so this is bounded above and below. So the range is going to be strict. You can't actually, it'll never be 8 and it'll never be 0. It's just always going to be between them. So it's going to be between 0 and 8. All right, and our last function here. So this is involving E, and again, you know, E or whatever, it doesn't really matter. It's still going to behave exactly the same way. So you just go 1. You have a horizontal asymptote on the right side of y equals 20. Again, this as x approaches infinity. So let's scale our axes. Let's count by I guess 4, because I don't think I even have 20. So 4, 8, before 4, oh sorry, I'm counting by 2. Let's call this 4, 8, 12, 16, 20. So I think it's just write a 4, 8, 12, 16, 20. And we also know that our x-axis will always be a horizontal asymptote on the left side. And so we'll state it for fun. We have a ha at y equals 0 as x approaches negative infinity. And lastly, the y-intercept is f of 0, which equals 20 over 1 plus e to the 0 power is 1. So 2 equals 20 thirds, 1/3 of 20, which is going to be 6 2/3. So it's going to fall somewhere between 4 and 8. Let's do our graph in red. This is 6, and let's just put it right here. Again, this is a sketch. And then we do this. And there you go. Logistic curve. So yeah, there's I'm sure you'll see some other examples of this. The logistic growth function is definitely would have a lot of applications, as as do exponential functions as well. Anyway, I hope that video was helpful, and good luck.